Hello, I'm Timothy, and I'm a third-year student majoring in mechanical engineering at CU Boulder. Today, we are going to learn about the variety of materials used by engineers in the design and construction of structures, such as modern bridges. Have you ever looked at a bridge and wondered what it was made of and where the materials came from? Imagine a simple wooden board spanning a small stream. When someone walks over it, what would happen to the board? The board would bend downward in the middle. Would this same material be viable for a bridge over a large body of water? Probably not. The materials used for simple bridges, such as crossing a stream, show us how understanding the strength of different materials is crucial to the design and construction of bridges. When designing bridges, engineers must really research and understand the properties of the materials they have available in order to select the best options. The strength of the material is usually the first thing engineers consider. They also think about the cost, availability, and suitability of the material for that particular structure. In some cases, the speed of construction is a factor, and that can vary depending on the materials chosen too. What materials are commonly used in bridge construction? Steel and concrete are the most popular choices for modern bridge construction. Other materials include wood, iron, plastic, and stone. Before the availability of steel and concrete, most bridges were made of wood, rope, and stone. When humans became skilled at creating iron, a new material became available for bridge building. However, iron is a brittle material and can break suddenly without warning. So, people tinkered with it to invent a more refined iron called steel. Steel is a useful bridge material because of its high strength in both compression and tension. Steel is also a ductile material, meaning that it can be bent or shaped easily into different forms. While very strong and versatile, steel is also very expensive, so it is usually combined with other materials to maximize strength and minimize costs. Steel is a heavy material and thus reduces the allowable span of the member when considered for use as a beam. Concrete is another important material when it comes to building bridges. Concrete is made of cement, water, sand, and coarse aggregate. Combining cement and water makes a paste that coats the surface of the fine sand and coarse aggregate gravel rock. Through a chemical reaction called hydration, the paste hardens and gains strength to form the rock-like mass known as concrete. Concrete is a versatile material that can be shaped easily with the use of molds. While concrete is extremely strong in compression, it is extremely weak in tension. Engineers design with this in mind and make sure that there are no tensile forces in the concrete part. They can get around this by embedding steel in the concrete to handle any tensile forces. Nowadays, the majority of bridges are typically built using a combination of steel because of its tensile strength and concrete because of its cost effectiveness and compression strength. Structural engineers pay close attention to the material properties when designing bridge members. Stress is the applied load divided by the material area it is acting on, typically the cross-sectional area of the member. Strain is the elongation or contraction of a material per unit length of the material. According to Hooke's law, stress is dependent on strain in the material. The modulus of elasticity or Young's modulus of a material is a constant associated with Hooke's law. The modulus of elasticity indicates the stiffness of a material. Tensile strength is the amount of tensile stress that the material can resist before failing. Compressive strength is the amount of compressive stress that the material can resist before failing. A material that exhibits ductile properties can be subjected to large strains before it ruptures or fails. A material that exhibits brittle properties shows little or no yielding before failure. Engineers refer to strain-stress diagrams that graphically display all of these characteristics. In a stress-strain diagram for steel and concrete, the steel curve has a noticeable linear, straight region. The slope of this linear region is the modulus of elasticity. The endpoints of these curves represent failure. The concrete curve shows a steady increase in strain and stress before it ruptures. Concrete fails with little or no warning, thus it is considered a brittle material. Just before steel breaks, it experiences a reduction in stress while strain increases. This is seen on the steel curve as a negative sloping section of the curve. When steel fails, it presents some type of warning, typically in the form of large deflections. Thus, steel is considered a ductile material. Today, we learned that concrete and steel are the most commonly used materials in large modern bridges. Engineers consider all the advantages and disadvantages of materials when deciding which to incorporate into their bridge designs. Check out the lesson on the TH Engineering website and take a look at the associated hands-on activity, Breaking the Mold, to explore more on the strength of materials.